All right, and electronics, they need to go away, please. So we are going to, let's have a quick reminder. Just part of what we're going to do today has to do with where we're going back to a very basic idea that we've known for a long time. A number line. So we put 0 here. To the right is positive, and to the left is negative. So if we have points, if we have 2 points, so all we're doing is putting some kind of measurement on our line. If we have 2 points on a line, on a number line, so let's say I put a point here and a point here, and this should be -4. How do we figure out how far it is between those 2 points? Count. We can just count spaces, right? So if I count spaces, what do I get? 7. So if I call this, say, if we call this point A and this point B, we would say the length of AB, which we just write as AB, equals 7. So this means the length of segment AB. And how am I going to write the name of this segment? How do I name the segment AB? The endpoints with, what else do I need for a segment? Two letters, so I have the endpoints, A and B, and a line over the top. Does it need arrows for a segment? No. So I just need 8. So the length of segment AB we write AB equals 7. And sometimes you'll see it written as MAB, which means the measure of segment AB. And that we would need a segment here. Measure of segment. So these two things mean the same thing. That's how we find the length. So we count spaces. What else? How else could we find the length? Using subtraction. We can use subtraction. So I would do 3 minus -4, like so. Minus a negative is a positive, and we get 7. Can we ever have a negative length? If I measured something, if I measured this tabletop, could I say it's -5 feet wide? No. So we want our length always to be positive. So if we did our subtraction in the opposite direction, if we said -4 minus 3 equals -7, we still got 7. We just want our answer to be positive. So we change that to positive. So our length would be 7. So if we did our subtraction in the opposite direction, we got a negative number, we would know all we need to do is switch it to a positive number. So our length is always going to be positive. So that's really the basic idea of measuring length. So the important thing to remember is we write the length of a segment just with the endpoints of the segment. Say AB, the length of AB equals 7. We pronounce that the length of segment AB. And sometimes you'll see M segment AB, which means the measure of segment AB. We always get a positive number for length. And if we have our points on a number line, we just count spaces. Nothing new, nothing groundbreaking. Just kind of starting off with the very basics here. So the length, what we're thinking about with the length is just how far it is between those points. Really easy idea. Now in geometry, we don't always want to talk about the length of things. We want to talk about segments rather than the lengths of segments. But when we talk about segments, and we'll do this with all kinds of different shapes, we compare the lengths of segments, and if we compare the segments themselves, we have we use a different word, and we have a different symbol. So the word that we use is congruent. And our everyday definition, and we'll make this a stronger definition as we go on, is two things are congruent when they are the exact same size and shape. So thinking about what we just talked about with the length, when would two segments be congruent? When would two segments be exactly the same size and shape? Could I have two segments that are exactly the same size and shape? So what would make them the exact same size and shape? How do we know if two strings are the exact same size and shape? What do? Measure their length. So two segments are congruent when they have the same length. That's how we decide if segments are congruent. And it works both ways. If we know that they have the same length, we know that they're congruent. If we know that segments are congruent, then we know that they have the same length. So we're just talking about two different ways of comparing them. Our symbol for congruent is an equal sign with a squiggle over the top. So we would say, for example, AB, we wrote this. What this tells us is that we would say segment AB is congruent to segment CD. That's what we would say when we saw this symbol. And when two segments are congruent, we know they have the same length. When two segments have the same length, we know that they're congruent. The way we mark things to show that they're congruent, if we have a drawing, is if, for example, if I had say I have a triangle, and I want to say that two sides are the same, that two sides are congruent, I put little tick marks on it. The sides with the same number of tick marks would be congruent. So if I had a figure with more sides, so say I had something drawn like this, and we want these two sides to be congruent, so we put the same number of tick marks. These two sides we're saying are congruent, so I'm going to put 2 tick marks on each of those. So the sides with the same number of tick marks are congruent. And if I say these two sides of this triangle are congruent, I'm going to put 3 tick marks on it. So the sides, the segments with the same number of tick marks are congruent. They have the same length. So the same number of marks tells me that they are congruent. That's how we show when we draw pictures that things are congruent. And what we're saying when they're congruent is that they have the same length. It's really different ways of comparing. So when we compare segments, we say they're congruent. When we compare their lengths, we're comparing numbers. We're looking at numbers. So segments, we're looking at congruent. Lengths, we're talking about numbers. So everybody see how congruent and length are related. So lots of times we're going to talk about congruent shapes. We're going to talk about congruent angles, congruent polygons, congruent hexagons, all kinds of different things that we're going to say are congruent. And that tells us different things about the lengths and the angles and how they work with each other. We're going to use the idea of congruent a lot in geometry. So we measure length, counting spaces. We could also, the other thing I could do if we don't have a number line, I could lay a ruler down and measure. That would give us a length. So we have a pretty good idea of how we work with length. What we want to talk about next is how we put segments together. We can use shorter segments to build bigger segments. And we can use that idea to figure things out about shapes. So everybody good with what we're talking about so far? All right. So the important idea, one of the big ideas from this section is our new postulate. Segment addition postulate. So let's remember what we said a postulate was. We talked about postulates yesterday. What is a postulate? Something that what is it, Sam? What do we do with postulates? Well, we talked about postulates that had to do with intersections, but okay, that's a postulate, yes. But I want to know what are we saying a postulate was? We know it's true. Sorry, I'll get you guys next time. With something that we accept as true without proof. So we're going to accept this idea as true without proof. We can't prove it, but it makes so much sense we're going to say that it's true. So we have a segment. We'll write it in words and then we'll draw a picture. It makes a lot of sense when we draw a picture. So we have segment PQ. And on this segment, point R is between P and Q. When this happens, we can say that PR is the length of segment PR plus the length of segment RQ equals the length of segment PQ. So here's our picture. Let's draw a segment. Here's my segment. Oops. This, and then we'll do that. So there's my segment. I'll make these points bigger. Here's segment PQ. Hello. Yes. So point R is between P and Q. So here's point R. So what this is telling us is the length of PR plus the length of RQ equals the length of the entire segment. Makes sense, right? The two smaller pieces, when I put them together, I get the big piece. That's what the segment addition postulate tells us. I can add the lengths of the two smaller segments, and it gives me the length of the longer segment. And all we need is for point R to be in between the two. So that's saying, for example, just an easy example, if we have this, here's my segment. If this is 7 and this is 3, how long is segment PQ? 10 units, right? That's all we're saying. If I have, let me write this up a little different, and then we'll make this just a little more interesting. So let's say this is P, this is Q, this is R, and we know the whole thing is 12, and that segment is 8. How long is segment PR? PR has to equal 4. The two pieces have to add up to the big piece. So that's what the segment addition postulate is telling us. And remember here we're talking about the lengths of the segments. We're adding the lengths of the segments. Now, of course, in math, we like to use numbers, but we want to make it more interesting. So we're going to do the segment addition postulate with variables. So let's look at a couple of examples of those. So everybody good with what the segment addition postulate is telling us? You can just add those two pieces together, get the big piece. All right, so let's look at a couple of other examples. We want to make this more interesting. So here is my segment. Put the endpoints here, and we'll call this segment L. The point in between is M, and this point is N. We know the whole thing is 32 whatever is long, 32 inches, 32 feet. This piece is 3x plus 8, and this piece is 2x plus 4. There's our favorite thing in math, x. And we want to find LM and MN. So we want to find the length of segment LM and the length of segment MN. So what are we going to do? We need to find x. So first we have to find x. So we'll make a plan here. So find x. How are we going to find x? What do we need to do to find x? So find x is the big picture. What do we need to do to find it? What do we have here? We have segments, right? We have smaller pieces. And then we have the whole segment. So what do you think? Okay, well you're kind of on the right track. What do you think? 3x plus 8 equals 32? You're almost there. You're almost there. Doesn't the whole thing, Marie?
Yeah. Is it where you put 3x plus 8 and then you add it to 2x plus 4 and then put it equals everything?
Right, we have to add the two smaller pieces to get the bigger piece. So find x. So I'm going to write here, add small parts to get the big part. So that's, find x is our big picture. We're going to do that by adding the small parts to get the big parts. So we're going to say 3x plus 8. That's this piece. Plus this piece. 2x plus 4 has to equal the length of the whole segment. Equals 32. All right, now we know how to do this, right? What do I have to do here? Combine like terms. Very nice. So 3x, what do I combine with 3x? 2x, and that equals 5x. And what are the other like terms? 8 and 4. Combine those and I get plus 12 because I'm adding those, and that equals 32. Next step, subtract 12 from both sides. So I get 5x equals 32 minus 12 is 20. Next step, divide by 5. I'm almost there. X equals 4. All right, I'm done with the problem, right? No. The problem doesn't say find x. The problem says find LM and MN. So what do I have to do those? Plug in 4 for x. So to find what the problem actually asks us for. So LM, the length of segment LM, equals 3 times 4 plus 8, which is 3 times 4 is 12 plus 8 is 20. And MN, do I need to plug in for x to find MN? If this piece is 20, the whole thing is 32, what does MN have to be? 12. We could check our work. We could say, we could plug that in and make sure we did it right. 2 times 4 plus 4. 2 times 4 is 8, plus 4 is 12. So we did it right. And 20 plus 12, to check our work, is 32. We're good. So that's how we're going to, this is more how you'll see the segment addition postulate used, is you'll be given problems like this. Does anybody have any questions about what we did here? All right, let's look at another example that asks the same kind of question in just a slightly different way. What if the problem were given to us this way? We'll call it L, M, and N. What if we know that this is 20? This is 3x plus 8. And we know this whole thing is 5x plus 12. What if it gives us the problem this way? What do we do here? Is this any different? No. We still add small parts to get the big part. And then we can find x, and then we can find our segment lengths. So what are the two small parts this time? 3x plus 8 plus 20 equals the big part, equals 5x plus 12. And then we do the same thing. So if we had the problem this way, what would we want to do next here, Matt? How would you, for this problem, what would you do next?
Subtract 3x.
Okay, we could subtract 3x from both sides. Get all the x's on one side. And can I combine these two? So I have 8 plus 20 on this side equals 5x minus 3x is 2x plus 12. And I can add these two together, right? 28 equals 2x plus 12. Now we're almost done. Subtract 12. 28 minus 12 is 16. That equals 2x. Divide by 2. And I'm back where we were before. X equals 4. And I can find the other pieces. If the problem had asked us to find the other pieces, I could find the other pieces. Same problem, just asked in a different way. Yes?
116 divided by 2 is 8.
16, yes. Thank you. 8. Was that where we were before? We were at 8. Okay. What did I do? Take the square root of 16? But same problem, just asked in a different way. Add the small parts to get the big part. That's what we do with the segment addition postulate. That's kind of the everyday way we could think of these kinds of problems. Add the small part to get the big part. All right. One last thing to talk about today, and then we'll be done. Midpoint. So when I say the word midpoint, what do you think of? What do you think we're talking about? The middle point, exactly. It's a point in the middle. So what does the midpoint, if we have the midpoint of a segment? What does the midpoint do to the segment if it's in the middle? What is the if the midpoint is in the middle, what does it do to the segment? Cuts it in half. Perfect. The midpoint of a segment cuts it in half. Oops. Press my eraser. Midpoint of a segment cuts it in half. So we can say this in a little more technical, now that we have some more vocabulary. We can say divides a segment into two congruent segments. So we're using our vocabulary, we're making it a little more technical. We're kind of starting to learn how to speak the language of geometry. So when the problem asks you about dividing into two congruent segments, you can think, oh, that's the point in the middle. So we're learning to speak geometry is what we're doing here. When a segment is cut in half, we say the segment is bisected. So bisect is the same as cut in half. So when we cut something in half, we say we bisect it. Whatever is cutting the segment in half is called the bisector. Thank you. So if a point is cutting the segment in half, that point is the bisector. If we have a line that cuts a segment in half, that line is called the bisector. If a ray is cutting a segment in half, that ray is called the bisector. So anytime you see the word bisect, you know it means it has something to do with cutting in half. Whatever is cutting it is called the bisector. So when we cut something in half, we bisect it. Whatever cuts it in half is called the bisector. And we're going to do the same thing with midpoint. Same kind of problem with midpoint as we did with segment addition. Just they're just a touch different. Same idea, just a little bit different. So everyone understand what we mean by midpoint and bisect? Okay, pretty easy ideas. All right. So let's look at an example that has to do with a midpoint. So your problem might look something like this. Might say that, and we'll call this R, S, and T. S is the midpoint of segment RT. And we're going to label this 7x minus 3 and 3x plus 1. And the problem tells us find RS and ST. So, similar kind of problem. We just do it in a slightly different way. So, what do you think we're going to want to do here? Same idea, we still have to find x, but we do it in a little different way. S is the midpoint, so what does it do to this segment? Splits it in half. So what does that tell you about these two parts? They're equal. They're equal. They have to be the same length. When it's split in half, the two parts are equal length. So what are we going to do with these two things? Make them equal. Very nice. 7x minus 3 equals 3x plus 1. They're the same. We can say they're equal. The lengths are equal. So now we can do our problem like we did before. So what do we want to do next? Subtract 3x from both sides. Okay. 7x minus 3x is 4x minus 3 equals 1 plus 3. So 4x is 4 and x equals 1. We're done. Right? No. What does the problem ask us to do? Find RS and ST. Didn't say find x, it says find RS and ST. So what do I do with x? Plug it in. RS equals 7 times 1 minus 3. So 7 minus 3 is 4. So RS equals 4. And if we did it right, ST is going to be 4 also. And we can check that. 3 times 1 plus 1, plugging in x there. So we did the problem right. So each segment length is 4. And we found the midpoint. If you get two different numbers, you probably did something wrong. And we could have the same kind of setup here where it gave us the length of the whole segment, and we needed to find the pieces of the individual pieces where we have a midpoint. Same kind of problem, but we just set the two parts equal when we have a midpoint. That's the difference. When we have segment addition, we add the two small parts. When we have a midpoint, we're setting the two parts equal. Same kinds of problems, just slightly different setup. All right, questions on that? All right. So we'll pass your folders back.